In this video, we'll see how to compare different age standard cycles like Otto cycle and Joule cycle and Diesel cycle when they are subjected to some constraints. So you might have seen many questions in GATE, engineering services and civil services. The questions are something like this. So they ask you to do the comparison between these three age standard cycles. The questions are something like this. For same compression ratio and for same heat addition, so which cycle will have maximum efficiency or which cycle will give maximum work done? So these kind of comparisons. So when they are subjected to different types of constraints, so how to do the comparison between these three age standard cycles, we'll see one by one. So here in this video, we will compare the three age standard cycles when they are subjected to the same compression ratio and the same amount of heat addition. So you can do this comparison easily by drawing these three cycles in a single diagram in both PV and TS coordinates. So let us try to draw these diagrams in this PV and TS coordinates. So here this comparison is for same compression ratio and for same heat addition. Compression ratio is constant in all the cycles and heat addition is also constant in all the cycles. For these two constraints, how this Otto cycle, Diesel cycle and Joule cycle are going to behave. So first I am drawing PV coordinates. So this is pressure versus volume coordinate. And here I am drawing TS coordinate. Temperature versus entropy coordinates. So first I am drawing this Otto cycle. You can draw any cycle. So first I am drawing Otto cycle. In Otto cycle, we will be having reversible adiabatic compression process, constant volume heat addition process. So then we have reversible adiabatic expansion process and constant volume heat rejection process. Cycle looks something like this. So 1 to 2 is reversible adiabatic compression process and 2 to 3 is constant volume heat addition process and 3 to 4 is reversible adiabatic expansion process and 4 to 1 is constant volume heat rejection process. This is the cycle. This is Otto cycle. And these are the four processes that are taking place in Otto cycle. I am drawing the same diagram in TS coordinates. So in TS coordinates, the diagram looks like this. So 1 to 2 is reversible adiabatic compression process, or we also call it as isentropic compression process. It's an isentropic process, entropy is going to remain constant, and it's a compression process, temperature increases. So 1 to 2 is isentropic compression process. So entropy remains constant, and it's a compression process, temperature increases. So 2 to 3 is constant volume heat addition process. It's a heat addition process. During heat addition, entropy is going to increase and temperature is also going to increase. So 2 to 3 is constant volume heat addition. During heat addition, both temperature and entropy is going to increase. So this is 3. And 3 to 4 is isentropic expansion process. Isentropic process, entropy remains constant, and it's an expansion process, temperature falls. So isentropic, entropy remains constant. Since it's an expansion process, temperature falls. And 4 to 1 is constant volume heat rejection process. It's a heat rejection process. From 4 to 1, both temperature decreases and entropy decreases. So whenever you are adding heat, both temperature and entropy increases. Whenever you are rejecting heat from system, both temperature and heat decreases. So temperature and entropy decreases. So this is how the diagram looks in both PV and TS coordinates. So here the comparison is between compression ratio and heat input. If you look at this compression ratio depends upon the volumes. And here in PV coordinates you have one volume coordinate. By just looking at this volume coordinate, we can easily do the comparison for compression ratio. And the second constraint is for the same heat input. So you can easily compare the heat inputs for different cycles in TS coordinates. We all know that, whenever a reversible process takes place, area under the curve So in TS coordinates for a reversible process gives you heat interaction for the system. So I can say like this, from 2 to 3, if you find area under the curve 2, 3 TS coordinates, so since 2, 3 is a reversible process, area under the curve in 2, 3, area under the curve 2, 3 in TS coordinates will give you the heat supplied. So by just finding out area under the curve, so we can say the heat interaction happened during that particular process. So for heat interactions, so we'll do the comparison in TS coordinates, and for compression ratio, we'll do the comparison in PV coordinates. So this is Otto cycle. Now I am drawing diesel cycle subjected to the same constraints for the same compression ratio. So inlet conditions for diesel cycle will also be the same, because the inlet conditions depend on the ambient. So ambient conditions are remaining the same, therefore inlet conditions for Otto cycle and diesel cycle are same. And the same compression ratio. Since you are compressing this by the same amount, I can say like this, from 1 dash I compress till I reach here, this is 2 dash. So 1 dash and 2 dash will coincide. 1 dash coincides with 1 because the inlet conditions for both Otto and diesel cycle are same, and 2 dash coincides with 2 because the compression ratio is the same. So I can say like this, so 1 dash will lie here and 2 dash will lie here. So it's compression process. And next process is, so in diesel cycle we go for constant pressure heat addition process. So this is a constant volume line. So this is constant volume line. So 2 to 3 is constant volume heat addition process. Whereas in case of diesel cycle, we will be having constant pressure heat addition process. So I can say like this, in TS coordinates we have already seen that. So constant volume lines are more vertical in comparison with constant pressure lines. Slope of constant pressure lines is less in comparison with the slope of constant volume line. So now I go for constant pressure heat addition process, 2 dash. So 3 dash is constant pressure heat addition process. So 3 dash will lie somewhere over here, and area under the curve 2 dash, 3 dash will give you the heat interaction. So here I am saying that, so for the same amount of heat supplied, in Otto cycle if you see the heat supplied is nothing but area under the curve 2, 3. So if I project this 2, 3 and if I find the area under this curve 2, 3, that gives you the heat supplied in Otto cycle. If you want to have the same amount of heat supplied in case of diesel cycle, so I am missing out this area. To compensate the area that I missed here, I am slightly extending here. If I find the area under the curve, this blue color line, that must be exactly same as area under the curve 2, 3. So I get 0.3 dash here. Now you can see here, this 2 dash, 3 dash line is going to intersect 3, 4 line. Now see here, 1 dash, 2 dash is isentropic compression process. Then I go for constant pressure heat addition process. I have gone for constant pressure heat addition process such that you can see, so this 2 dash, 3 dash line is intersecting this 3, 4 line. This is constant pressure heat addition process. Then what I do is, so once heat addition is done, then I go for expansion process. So till I reach the initial volume. Till I reach the initial volume, I go for expansion process. Once expansion is done, I go for heat rejection process. So constant volume heat rejection process. So till I reach the initial state. So since I want to come to the initial state, it's a cyclic process. I expand till I reach the initial volume. So if I go for further expansion beyond this point, if I go for constant volume heat rejection process, it will not be a closed cycle. So if I want to get a closed cycle, so I need to expand until I reach the initial volume. So then I go for constant volume heat rejection process. I can say like this, so 4 dash is going to lie here. So 1 dash, 2 dash, 3 dash and 4 dash, 1 dash. So this is your diesel cycle. So this is 3 dash, so I expand this, I go for reversible adiabatic expansion process. So till I reach this constant volume line. Once I reach the initial volume, so I go for heat rejection process, constant volume heat rejection process. So till I get the initial state. And it's a cyclic process. So this is how your diesel cycle and your Otto cycle will look when they are subjected to the constraints. The constraints are same compression ratio and same heat addition. Now in the same diagram, so if I try to draw this dual cycle, for same compression ratio, inlet conditions will depend on the atmospheric conditions. So atmospheric conditions are remaining the same, therefore the inlet condition for dual cycle will also remain the same. Therefore, state 1 double dash will be same as 1 dash, and that's same as 1. I go for compression process. So since it's for same compression ratio, so 2 dash, 2 and 2 double dash will be coinciding. So 1 dash will lie here and I compress the gas. So 2 double dash is lying here, 1 double dash and 2 double dash. So this is for same compression ratio. So then I go for constant volume heat addition. In dual cycle, so first we go for constant volume heat addition, and after that, so we go for constant pressure heat addition. So since this is a constant volume heat addition process, so it will coincide with the earlier constant volume line. So this is constant pressure line, it's for diesel cycle. So for dual cycle, first we will be having constant volume heat addition process, therefore this red color line will coincide with the black color line. And after this point, I am calling this point as 3 double dash. After this point, so we go for constant pressure heat addition. So since constant pressure line slope is lesser than constant volume line, the red color line will come below the black color line. So this is constant pressure heat addition process. So this goes so till I reach 3 double dash. So already I told you that. So we are going for same amount of heat addition. I mean, whatever the area under the curve, black color curve we are having, we should have the same area under this red color curve also. So whatever area I am losing here, I am compensating that area by just extending so this point beyond this black color line. So from here I go for so expansion process, reversible adiabatic expansion process till I reach the initial volume. Once I reach the initial volume, so then I go for so constant volume heat rejection process. I go for heat rejection process so till I reach the initial state and the cycle is complete. So first I go for constant volume heat addition process. This I am calling it as 3 double dash. After constant volume heat addition process, so then I go for constant pressure heat addition process. So I am calling this as 4 double dash. Now you can see this 4 double dash and 5 double dash curve is intersecting this blue color curve. Blue color curve is 2 dash, 3 dash. So this 4 double dash curve and 5 double dash curve should intersect this 2 dash, 3 dash line. So it should pass. And this I am calling it as 5 double dash. I expand till I reach the initial volume, and then I go for constant volume heat rejection. So till I reach the initial condition. So these are the 3 cycles. So when they are subjected to for same compression ratio and for same heat addition process. Compression ratio depends on volume. So volume coordinates are in PV coordinate. So we do the comparison for compression ratio in this diagram. And heat input depends on area under the curve in TS coordinates. So heat comparison, so we do here. Whenever you want to do a comparison for pressure and volume, we do in PV coordinates. Whenever you want to do comparison for heat and so maximum temperature or minimum temperature, we do that comparison in TS coordinates. And from there, we try to complete the cycle. Now I completed the cycles. So if you look at this black color one, so if you look at this cycle, 1, 2, 3, 4, 1. So this is Otto cycle. Otto cycle. And if you look at the cycle, 1 dash, 2 dash, 3 dash, 4 dash, 1 dash. This cycle is diesel cycle. And if you look at the cycle, 1 double dash, 2 double dash, 3 double dash, 4 double dash, and 1 double dash. This is dual cycle. Dual cycle. These are the 3 cycles. And if you want to do the comparison, you can do the comparison for 3 cycles. Which cycle will have maximum efficiency? Now you can see, so one thing is clear, for all the cycles, heat supplied is remaining constant. I can say like this, heat supplied for Otto cycle is the same as heat supplied for dual cycle is same as so heat supplied for diesel cycle. Diesel cycle. If you look at this curve, 4-1 process, you can see this is a right to left process in TS coordinates. Area under the curve in TS coordinates will indicate so heat transfer. So if the process is from left to right, it is nothing but heat supplied to the system. If the process is from right to left, it is nothing but heat rejected from the system. So you can see area under the curve 4-1 gives heat rejected. So 4-1 is for Otto cycle, area under the curve 4-1 gives heat rejected in Otto cycle, and area under the curve 5-1 gives heat rejected in, so 5-1 gives heat rejected in dual cycle, and area under the curve 4-1 gives heat rejected in diesel cycle. And you can see from the diagram it's very clear, area under the curve 4-1 is small than area under 5-1 than, so 4 and 1. I can say like this, heat rejected in diesel cycle is more than heat rejected in dual cycle. Is more than heat rejected in Otto cycle. So heat rejected is more in diesel cycle, and you can see heat supplied is same in all the cycles, whereas heat rejected is more in diesel cycle. And if you look at work done, so work done is nothing but, so heat supplied minus heat rejected. So heat supplied is constant for all the cycles. So whichever cycle is having more heat rejected, so that will have less work done. For diesel cycle, heat rejected is more, therefore I can say like this, work done by diesel cycle is the least. And the next comes, so work done by dual cycle, and the highest is, so work done by Otto cycle. In Otto cycle, the heat rejected is less. So for the same amount of heat supplied, since work done by Otto cycle is more, I can say like this, so efficiency of Otto cycle is more than, so efficiency of dual cycle is more than efficiency of diesel cycle. So when the three cycles are compared for same compression ratio and for same heat input, Otto cycle will have maximum efficiency and diesel cycle will have least efficiency. And if you look at the heat rejected, so heat rejected is more for diesel cycle and heat rejected is least for Otto cycle. So these are the conclusions which you can make out.